Okay. So good afternoon, everybody. First of all, thank you all for joining this course, and I hope you are all enjoying this. Now, this is our first live session. Basically, it is partly to clarify any of your queries which have kind of a broad interest, and also to give you additional information about related to the topics that are covered in the course. Okay, so I hope you can see the slide that I have shared. Okay. So first of all, I will do two things in this particular interaction. One is to take up your specific questions. So there are a couple of questions which are asked by some of the participants, and there were also some queries which were in the forum which could be of general interest. So these are the two things that we would take up. So first of one of the questions that specific questions which you asked is whether the protons and neutrons pair in the nucleus. I mean, that question was framed like that. I think the question is addressed to the shell model kind of situation, where we consider the neutrons and protons separately in potential, in a particular potential, and then consider their energy levels separately. And if the question is like, should we consider the electrons and protons pairing of the electrons and neutrons, then answer is no, in the nuclear models that we have been considering. Okay, so the protons and neutrons are considered separately. There is no pairing between the protons and neutrons that way. If that is not the question, I mean, I would be happy to answer once you clarify what exactly the question is, either through this chat or later through email or forum or wherever. Okay, so the other one of the things that were not very clear to many of you, as we understand through your discussion in the forum, is the angular momentum additions. This may be because I had kind of assumed quantum mechanics basics being as a prerequisite for this course. So some of you may not really have gone through that. In that case, it may be a little bit confusing to you to understand what is the angular momentum addition, how is it applied in the case of, say, for example, alpha decay or gamma decay, etc. So let me spend 5-6 minutes on that here now. Okay, and if you have further questions, then we can certainly discuss that in the forum, or I can consider some explaining it to some kind of a small short note and then circulating it if required. Anyway, let me explain as much as possible now. So in quantum mechanics, angular momentum, spin, etc. is taken in slightly different compared to what we consider in classical mechanics. For example, if we have angular momenta of two systems, okay, I1 and I2. These could be, for example, the two different nuclei, or electrons, two different electrons, or electron and proton, or two protons, or any such systems. In particular, in our case, we would be actually talking about nuclei. So let's take two such things. Let us have I1 as the angular momentum of one of those, and I2 as the angular momentum of the other one. Intrinsic angular momentum is called spin in quantum mechanics, and so this would, in the nuclear systems, correspond to the nuclear spins. So if we actually think about combining them or considering them as a single unit, then what would be the angular momentum of the combined system? Quantum mechanics prescribes that it cannot be predicted completely. It cannot be a particular specific value. It could be one of the possibilities, and the possibilities are listed in a very clear way. So the possibilities are the difference between the two angular momenta, the modulus of that. So you don't have to worry about which one is larger and which one is smaller. Take I1 minus I2 and the modulus of that. That and I1 plus I2. I1 plus I2 would always be larger compared to I1 minus I2 because both I1 and I2 are positive numbers. So you can have the angular momentum, any value between I1 minus I2 modulus of that and I1 plus I2 differing by 1 unit. For example, if you take I1 equal to 1, I2 equal to 2, then I1 minus I2 is equal to 1 and I1 plus I2 equal to 3. So you can have angular momentum of the combined system either 1, 2 or 3. All these three are possible. Let's apply this in the case of alpha decay now. Okay. Let's consider, say, for example, you take a nucleus X decaying to Y and an alpha particle. And let's consider the angular momentum of the right hand side. The right hand side, we have the daughter particle, daughter nucleus Y. Let's consider the angular momentum corresponding to that as Iy. Then the angular momentum of the alpha particle, we denote it by I alpha. Relative, then there is also, whenever you have two or more particles, there could also be relative orbital angular momentum, because if they are moving with respect to each other, there could be angular momentum due to their relative motion. So these angular momenta are not intrinsic to those particles, but because of their relative motion, and these are orbital angular momentum, relative angular momentum uh, because of their motion. So here we have two particles, two systems in the right hand side, okay, y and alpha, and relative angular momentum is only one of that one, and that is, let us denote that by small l. And of course, the left hand side we have only one nucleus x, and the angular momentum or the spin of that we denote by ix. I alpha, the angular momentum or the spin of the alpha particle is experimentally given to be equal to 0. So it does not have any spin. So that makes life slightly easier in this case. So we have only two such things to add. So one is Iy and the other is the angular momentum or orbital angular momentum, relative orbital angular momentum between y and alpha. That is, so combining these two, you can have Iy minus L to Iy plus L differing by units of 1. These are the possible values of Ix that we can have. That's what quantum mechanics prescribes. So this is what you have to consider whenever we are considering the angular momentum analysis of alpha decay. Let us take a particular example. So Ix equal to 2 and Iy equal to 3, let us say. Then in that case, we can have, what are the values of L that are possible? That is the question that we can ask. Let's take L equal to 0 and then see if that is a possibility. You take L equal to 0, Ix could be Iy minus L to Iy plus L. L is equal to 0 means it's only equal to 3, and Ix is given to be 2, therefore L equal to 0 is not possible. So we cannot have that. L equal to 1, we can have Iy minus L between Iy minus L equal to 2 and Iy plus L equal to 4. So Ix equal to 2 is one of the possibilities in these things. So it's fine. If you take Ix equal to 2 and Iy equal to 3, L equal to 1 is a possibility. All right, that's how we consider this. And similarly, L equal to 2 also has a possibility to give you Ix equal to 2 when you consider the combination of Iy and L in the angular momentum. Similarly, uh, we can have I equal to 3, L equal to 3, L equal to 4, and L equal to 5. L equal to 6 is not possible because L equal to 6, Iy minus L is 3. You cannot have less than 3 there. So you cannot have less than 3 if L equal to 6 and Iy equal to 3. So these are the possible um, orbital angular momentum in this particular case that we can consider. Okay. All right. I hope that explains this analysis of the angular momentum in the case of alpha decay in particular, and in general for any combination of two particles or two spins combining to give you a single system. Okay. And as I said, if you have any further questions, one of the things that you should always do is to look up in your quantum mechanics books or anywhere else where it is discussed. And I think in the lectures also I have tried to explain this thing. Now go back and then see if you can understand it better. Then the other possibility is, other thing that you can do is to actually write to us if you have any specific questions on it. These slides, I guess we can post it for you. I will talk to the NPTEL office and then see how that can be done. Okay, you will have access to it. All right. So then the other thing is the parity consideration in this, which comes along with this one. So again, in quantum mechanics, associated with angular momentum L, the parity is minus 1 power L, which means that if L is even 0, 2, 4, etc., then it is even parity that is associated with that L, even L. And odd values of relative angular momentum will give you so if you have two systems with relative angular momentum, that would mean that their orbital angular the parity will be opposite if the angular momentum is odd. So here we can apply that. In this previous example, for example, L equal to 1, 2, 3, 4, 5 are the allowed L values corresponding to a nucleus X with Ix equal to 2 decaying to daughter nucleus Iy with Iy equal to 3. Okay, and there are different possibilities of parity. So the X has a positive parity and Y has a positive parity. In that case, L equal to 2 and 4 are allowed because it's the same parity. There is no change in the parity and their parities are the same. So in that case, L has to be even. Similarly, for I equal to, so Ix minus and Iy minus. So if the parities of X and Y are odd, both are odd, then also they are the same, and therefore only the even values of L are allowed. So 1, 3, 5 are not allowed in this case, and On the other hand, if one of this is, or their parities are opposite, either X is equal to X has a positive parity and Y has a negative parity, or X has negative parity and Y has positive parity. In both cases, the parities are opposite to each other and therefore L has to be odd. Odd meaning that 1, 3, 5 are allowed and 2, 4 are not allowed. Okay. So these are the things that we in this angular momentum addition case. Okay. So now let me see. There is a question. I have a small doubt about stability of the nucleus. Which one is stable, proton or neutron? Okay. Neutron is, so this is Shivakumar has asked this question. So maybe others also have the same question. Proton is stable. Proton is stable and neutron is not stable. A free neutron can actually decay. Free neutron can decay. In fact, a free neutron will decay and you don't see the free neutrons in the universe anywhere. Whereas protons are stable. Hydrogen nucleus is stable, and hydrogen stable nucleus is a single proton, and that is stable. In fact, that is very essential for the survival of hydrogen atom and all other chemistry that follows. I mean, nuclear physics and chemistry that follows, and this whole structure formation requires hydrogen to be so, or it has happened like that in the present universe that we have hydrogen very atom very stable. That is because the proton is very stable. Otherwise, we would not have been here. All these structures that we see would not be here. And this stability is guaranteed by what's called the baryon number conservation. That baryon number conservation and energy conservation. That's because the proton is the lightest baryon and it cannot decay to anything else because there is no lighter baryon there, and baryon number conservation will not allow it to decay to something which does not have any baryon in it. In fact, I had set this as one of the questions in one of the assignments, I guess. So basically, I have explained the answer to that. I hope you understand or that answers your question. If you still have questions, then let me know. Okay. All right. So now let me give you some kind of a general view on what this course um, has been talking about. I had explained this in the introduction a little bit, but let me explain that a little more here. And this would also be giving you a kind of a motivation for further the rest of the course from now on. I think now at the moment we are just starting at the particle physics part, and the rest of it will be basically not the nucleus but the nuclear physics part, but for the talking about the subnuclear particles and talking about the fundamental elementary particles and fundamental um, forces and dynamics there. So let me give a kind of a brief discussion on that part before we close today. Okay. So everything in the universe is, I mean, there are many variety of things that we see, but basically the idea is that everything can be thought about as made of some very few number of fundamental particles. Okay. For this is what we had been analyzing, and we know that atoms are made of nucleus now, and the nucleus is what occupied us for the past a few weeks. And we also know that the nucleus has protons and neutrons, and further, the protons and neutrons are composed of quarks. Okay, so we had zoomed into this part so far. We just started talking about the quarks, and then there is a question about the that are okay. Question about the dynamics that is related to this, that the forces coming into which come into play there. So one of the forces that we don't see otherwise, like in our day-to-day life, is the strong nuclear force. Strong nuclear force is required to actually hold the nucleus together. Rutherford told us that nucleus is focused and concentrated in a particular small volume of the entire atom, and all of the positive charge and almost all the mass of the atom is concentrated in this small fraction of the atom. And how does that happen? When protons all have positive electric charge, and we know that the like charges repel. So if they are concentrated in a small volume, then they should repel each other and fly away from each other. But that doesn't happen in a nucleus. How does that occur is what we understand by the nuclear force. There is a strong nuclear force which actually holds these things together. And there is also weak nuclear force which causes, for example, the beta decay. So these are not forces which can be actually understood in terms of electromagnetic interaction or gravity, etc. So these are entirely different. So these are two different independent forces that we have in nature. And in fact, in addition to the electromagnetic force and gravitational force, these are the only two other fundamental forces that we have in the entire universe. So we have four fundamental forces and a handful of fundamental or elementary particles, which actually builds, which makes all of the universe. Okay. The natural question is that if protons are made of quarks, then and neutrons are made of quarks, are there other particles which are made of quarks? So this question was then followed by many people in the beginning of the 20th century, and it was started by Victor Hess, and he discovered that there are many particles, many charged particles that's coming from outside the Earth, extraterrestrial. He called it cosmic rays. So these cosmic rays had charged particles and many particles. Many of the exotic particles we would discover in these later on. So, and Robert Millikan actually categorized these cosmic rays, saying that 80% of this is basically proton, and then helium nucleus is also there, which is basically alpha particle, and a little bit, very small amount of heavier atoms. So, and the electron-like but positively charged particle was also discovered, and later we realized that this is basically what the antiparticle of electron, which Dirac had proposed. So this is called the positron, and it has the same charge, same mass, and as that of the electron. Electric charge is opposite to that of the electron. And then muons, which behaved like electron, were also discovered, but much heavier than the electrons. Then there are many other particles like pions, kaons were also discovered in these cosmic ray experiments. So at some point of time, in the second half of the 20th century, there were a lot of particles like this, extra exotic particles, and which are not really part of any of the matter that we see around, common things, but coming from or present in the nuclear in the cosmic rays or in the cosmic ray interactions with the upper atmosphere. Okay, so at that time the idea was to understand what's going on with all these things, and that's where Murray Gell-Mann and the other people at that time, mainly Murray Gell-Mann, actually proposed that let's classify this in this particular fashion. There is some order in which we can actually put them together, can classify them. For example, the neutron and proton can be considered as a kind of a group or belonging to a particular group. Then there were other particles which could be grouped like that. And then he made some kind of an eightfold way, as it was, to categorize these mesons, which are lighter, and baryons, which are heavier. Both are made of quarks. Well, mesons are made of quarks and antiquarks. Okay. There are many others. Then this quark model could actually explain all these eightfold way that Gell-Mann had put up. In fact, Gell-Mann himself was the one who coined this word quark, and then he explained that we could actually think about all these particles are made of these quarks. Later on, we discovered the quarks as elementary particles. So this is how the studies were done, and all these particles which we had seen could be actually understood as made of quarks, and there are some symmetry principles behind these quark model which allow us to categorize them in the groups of this 8, etc. Okay. Again, if you want to know more about it, you can look up in any book which discusses what's called quark model. Any elementary particle physics book, including that of Griffiths, you can take up and then try to understand. Okay. So to cut the story a bit, short, then we have now these elementary particles: electrons, muons, and tau leptons, okay, which are charged leptons, very light compared to other particles. Then there are 3 neutrinos, one neutrino corresponding to electron, then which comes in the beta decay. Similarly, in the muon decay, we can see another neutrino. We know that they differ from the neutrino which is coming in the beta decay when we consider them in other reactions. So this has been now established that the neutrino that comes in the muon decay, there are 2 neutrinos which comes in there, but one of those things is different from that is associated with the beta decay. Similarly, the tau lepton is also discovered, and its decay, and it's associated with that tau lepton, we have a tau neutrino. Among the quarks, there are 6 quarks, the U quark and D quark. That's enough to actually make neutron and proton and all matter that we see. In fact, all matter that we see can be explained by just what's highlighted in this purple color here. Okay, the first column: electron, U quark, and D quark. That's all what takes to make all elements. All elements are made of these 3 things, and it's in a way very, very amazing, because the variety of things that we see around terrestrially and the things that we see in the universe otherwise, all the stars and anything that you see, you can see in the universe, anything that we have observed in the universe, all of these structures are made of these U quark, D quark, and an electron. That's all. All other particles like muon, C quark, S quark, T quark, B quark, etc., are all highly unstable, and particles made of these are also unstable, but they are all needed for consistency of the dynamics. So the dynamics actually dictates that these things are there. Well, I mean, that is how that is one way of understanding it. The other way would be actually to say there, therefore the dynamics was like that. Whatever way that we see, but the way that we have understood the dynamics, it's essential for the theoretical construction to have all other particles, which does not mean that all those particles are just fictitious particles. They are all discovered. How are we discover? How do we discover that? We discover that not in commonly seen part objects, but we can see them in reactions where we actually can create them. They can be made, and they can be they decay away after that. But so in the cosmic reactions or the interactions of the cosmic rays with the upper atmosphere can also create them. That's how we detected them in the first place, many of them, in the balloon experiments and other cosmic ray experiments. So, and some other things like the tau lepton was discovered in the accelerator based reactions where we have charged particles which actually combined together and then reacted together. And these reactions will actually have high energies, high enough energies to produce these elementary particles, and then we can understand the dynamics. Okay. There are also these W bosons and then Higgs boson, etc. We will come to those things later in our course, a little more deal with them in a little more detail. They are all part of the dynamics, and in short, W and Z are like the photon, the radiation, electromagnetic radiation that we have. So these are the corresponding things in the weak interaction case. So strong interaction case, we also have the gluons. We'll talk about these particles in a little more detail later. Okay. So this is what I was telling actually. Everything that we have is made of these three particles. All right. So the dynamics also is we have now understood through what's called the quantum field theory. Okay. Basically, in quantum mechanics, if you consider the quantum mechanics, it's not possible to. It can explain very well the atomic level reactions, how atoms combine to form molecules, etc. But when it comes to processes or phenomena like beta decay, where new particles are created, say electron, antineutrino, neutrino, etc., are created from the nucleus where they are not present otherwise, we need what's called the we had to go beyond the quantum mechanics, the usual quantum mechanics, and we can consider we had to understand them through different mechanisms which is incorporated in what's called the quantum field theory. We will not discuss that here, but some of you who are taking this direction further in your higher studies will certainly encounter this. And it's a mathematical uh, framework which explains how the dynamics of the elementary particles work out. But we will not be going into the details of that here. I guess we will actually talk a little bit about the results coming from that, but not really the quantum field theory part. Okay, this part may be a little more useful to you as far as the course is concerned. How one particular reaction we consider as allowed and not allowed. There are basically various different symmetry properties that we have to consider. One is energy conservation, certainly, then angular momentum conservation, and then there are other symmetries that we have to consider, other quantum numbers that has to be also considered. So let's take an example of this beta decay. The neutron goes to proton and an electron, but that itself is not really enough. Okay, experimentally, energy measurements actually showed that this is not the case. In fact, even the angular momentum consideration should have shown us that it is not so. Once we know the spin of the electron is half, we cannot actually get this neutron with spin half, proton with spin half, and electron with spin half is not sufficient to actually add up the way that we describe the angular momentum additions. There has to be another spin half particles. Okay, so that is one thing. Even energy consideration would tell you that, and that is where Pauli actually proposed a missing particle, a particle which has no mass, its mass is very small and neutral, so that we don't see it. We cannot actually, our detectors won't be actually seeing it. So that is a missing particle. So this is okay. This we can actually take up. So here you can see N is a baryon, P is a baryon. So a baryon going to a baryon, that conserves the baryon number. But in the case of the first one, there is an additional quantum number which is called the lepton number. The lepton number for electron is 1, and proton it is 0, neutron it is 0. Therefore, the first reaction is not possible even considering the electron number. But second one, if you consider, once you introduce this neutrino, it has to be an anti-neutrino, because the lepton number consideration would tell you that L equal to 1 for electron, L equal to the lepton number equal to -1 for the anti-neutrino. Therefore, that's going to be equal to 0 on the left hand side and right hand side. So that's okay. So let's take another example where N going to, instead of the proton, you consider another positively charged particle which is lighter than neutron, and everything is okay. Here X lepton number is also conserved, but it's a meson, and N is the neutron is a baryon. So the N going to a pi plus and no other baryon is not possible. The neutron decaying to 5 plus E minus nu bar is not possible. Okay, baryon number is not conserved there. And again, as I said, it has to be an anti-neutrino, not a neutrino itself. Anti-neutrinos we denote by a bar above this, see, above their symbol. And in this case, electron and neutrino both have lepton number +1. Therefore, they will add up to +2, and N equal to 0 on the left hand side, and right hand side we have 2. That way it is not conserved, so this is not possible. And the last one is, you cannot, I talked about different types of the neutrinos. Okay, the one is electron type and the other is muon type. So can it be mu antineutrino? That's not possible, because in fact the lepton number comes with these flavors. Le has to be conserved separately compared to the mu, L mu and L tau. So here that is not conserved again. If any of you have any confusion with these things, please let me know. I'll be very happy to explain or point out to you to the literature where you can actually learn more about this. Okay, so yeah, I have written a few more reactions here where we have some of these. Yeah, I think only the lepton number is not conserved, and where everything is allowed. Okay, so one is this beta decay itself, which we saw just now, but similar to that we can actually take tau decay. The tau decay to mu minus anti-neutrino of mu and neutrino corresponding to tau. That is perfectly all right, energetically all right. Angular momentum is okay, and all the other quantum numbers like baryon number, everything has baryon number 0, so it's okay. Lepton number individual with individual flowers, that is also conserved. Okay, there is no problem. At the quark level, we can think about all these things at the quark level. Leptons, we don't have any structure for them, but baryons, neutrons, and protons are made of quarks. We said that earlier. So neutron is made of a U quark and two D quarks, and proton is made of two U quarks and a D quark. So at the quark level, we can think about the beta decay as D quark converting to a U quark and an E plus, E minus, and an anti neutrino. Okay, so this is how we understand. All right. So I think basically these are some of the things that we have been going through, and some more details we will go through related, considering the elementary particles and then their dynamics. And in a larger context, these are very, very important. Understanding all these reactions are very, very important to understand the evolution, beginning and evolution of the universe. So, if we consider, it is more or less established now that the Big Bang cosmology is the right way to look at the cosmic evolution. According to that, the universe was formed in a kind of a very high energy and high density and small form, and then it was expanded and cooled, and then the temperature came down, and then many other elementary particles, so the radiation actually became to elementary particles created from that, and then there's elementary particles are exactly the same elementary particles that we have been talking about here, all the quarks and leptons. They were all created, and then they formed structures. They formed structures as the universe cooled. That's how we understand this. There are very precise calculations, theoretical calculations used based on the quantum field theory and other mathematical formulations, and there are experimental tests to verify these things. So this is where we stand now. So essentially, but there are also various things that are not completely known. So the evolution of the universe in the structure formation is kind of understood quite well from a point like something like the formation of the nuclei onwards, or slightly before that also. Like maybe beginning from the electro interactions, like that's where the particle physics comes in, that as we discuss in this course comes in, and all this dynamics goes in there, and in the structure formation, structure meaning whatever structures that we see in the universe, including all the galaxies, galactic structures, groups of galaxies and everything, and the structures of the planetary system, including us also. So that is all very well understood, but at the same time, there are a few things that we have not few things, but very fundamental things that are clear to us and that we don't understand. For example, there's something called dark matter, which are required for the structure formation as we have been seeing, as we see in the universe. If we consider the Big Bang nucleosynthesis and Big Bang the cosmic picture as we see from the Big Bang cosmology. We still don't have any kind of a candidate for dark matter. So we will talk about some of these things too in maybe the next or the last session. Okay. But that's kind of the motivation to study the particle physics beyond whatever we have been explaining in this course and then in your higher courses that you will encounter later. Okay, so I think I will stop here, and then if I don't see many questions, but if you have any questions, we can actually look at it, uh, post it in the forum as well, and or send us an email. We will be able to then discuss that. Okay, thank you.